Hi there. Today I'd like to talk about the fourth of Maxwell's equations, the Ampere Maxwell Law, which is that the curl around a loop of the magnetic field is equal to the current density plus the rate of change of electric field in that surface. It's easiest to explain if first of all I just look at Ampere's law, and then we'd have that B dot dl was the electric field, the magnetic field around a loop, and that would be equal to, imagine that going through, that would be equal to the current that goes through that loop. So that would be written as B dot dl, the magnetic field strength summed all the way around the outside of a loop that we're just imagining around a wire, equal to mu naught times the current that goes through that. Now, the current that goes through that is the same as the current density summed over this surface. If we imagine a surface with a current density J, then J summed over this surface is the same as the current that goes through that surface. So that's why instead of having mu naught I, here we've got the surface integral of mu naught J, where J is the current density on that surface. And this bit here is also mu naught times current density. Because if you remember Gauss's law was that E dot ds equals charge over epsilon naught. So if you had some charge Q plus, this might be a plus, and you surrounded it by a surface, then E dot ds through that surface would be equal to the charge enclosed over epsilon naught. So if you move that epsilon naught over to here, we have epsilon naught E dot ds is equal to Q, and then we do a rate of change of this. So we have the rate of change of epsilon naught E dot ds is equal to the rate of change of Q. You can see that this bit here, the rate of change of E dot ds times epsilon naught, is a bit like this bit up here without the mu naught, and that this really is a rate of change of charge, which is like current or current density. Let's let you see that properly. There you go. So this bit here is also very similar to this. It's basically just mu naught times current density, but it's current density caused by this rate of change of electric field. So that's how you can go from Ampere's law, where we've just got that the magnetic field strength around a wire can be found by using this relationship, that the total sum of the magnetic field strengths around this wire is equal to mu naught times the current going through the wire. So we know that for a circle that would be 2 pi r. So that's basically B times 2 pi r is equal to mu naught I. So that would be the relationship here. And you can go from this formula to this one by just noticing that if an electric field strength is changing on that surface, that also adds a sort of current density to the equation. Now this equation can be looked at over a big surface like this, or it can be looked at over a tiny, tiny surface, or even just a point, when you would say that the curl of B is equal to mu naught times the current density plus epsilon naught mu naught times the rate of change of electric field, which is just taking this, which is looking at larger surfaces, right down to a point. And this is sometimes also written with an H to be a rate of change of displacement. What we have here is the magnetic field strength in a material. When you are looking at magnetic field strength in a material, you have to take into account the magnetization of that material, and that's why you use H instead of B. And H is defined to be B over mu naught minus the magnetization. Thanks for listening. Bye.